Hello, pre-calculus honors students. Here we are with some limit theorems from 17-3. Now, basically, this starts off with sort of the plug and chug mentality. That is, the limit seems the same thing as evaluating a function at a certain point. Like the limit as x goes to 2 of 5x plus 1. We put the 2 in for x, and we get 11. Okay, seems pretty straightforward. And like all these limit definitions, if I've got the limit as x approaches c of fx equals L, limit as x approaches c of g of x equals m, then basically we're saying the limit as x goes to c of fx equals f of c, but got to be careful with this. This is only if f is continuous at x equals c. That is, here's f, here's c, here's f of c, and basically the function agrees, and the limit as we approach c of f of x equals f of c, then it's continuous there. It's not a sudden hole or sudden vertical asymptote or anything like that. And so basically a lot of these are based on this idea of distributing the idea of limit over addition or limit over division or multiplication, or constant multiplier comes outside the limit. And we'll be using these a lot in evaluating limits by hand. Also trig functions, as long as c is in the domain. Some trig functions are limited, aren't they? So the limit as x goes to pi over 2 of the sine of x is the sine of pi over 2, which is 1. And the squeeze theorem is going to be very important. And the idea behind this is if that f is a function between two other functions. So here's h of x, let's say, and here's g of x, like this. Two functions, and f somehow snakes in between these two. Stays in between these two, and it gets squeezed in between those two functions. Basically, we're saying then, if h and g, as x approaches c, approach this limit of L, then f will as well. So if you're given these, remember this is your given, all these ideas, that f is a function in between g of x and h of x. And actually I've got h of x as the lower one, so by in between f of x could be less than h of x and bigger than g of x. So basically f of x stays in between two other functions. And the two functions agree on a limit as x goes to c, then f has to go to that limit as well. That's the idea behind the squeeze theorem. Now there's a couple special trig limits that the squeeze theorem helps us prove. You know, if you try and do the limit as x goes to 0 of sine x over x, and you just try and plug and chug on that one, you get sine of 0 over 0, which is 0 over 0, which is indeterminate. It's not 0, it's not 1, it could be anything. But we're going to prove this. So you're going to memorize these two. Don't plug and chug on these because you keep getting 0 over 0. Memorize those two, and we're going to apply them in many situations. Here's a proof of the first one. If you look on the unit circle and you look at the areas here, or actually look at these segments here like this, this is the tan theta up here, and this is the sine of theta. And basically then we can come up with the area of these triangles by taking 1/2 base times height. In each case, this triangle here, the area of the triangle, small triangle, is less than the area of the sector, is less than or equal to the area of the big triangle. And the area of the small triangle is 1/2 base, so it's 1/2 the base 1 times the height, which is sine of theta. And the big triangle is 1/2 base, which is 1 times the height, which is tangent theta. And the sector here, remember the area of a sector is 1/2 r squared theta. Well, in this case, r equals 1, so you got 1/2 theta. And when you solve that out and divide through by sine theta, because in this case it's all positive, you get the sine of theta over theta is between cosine theta and 1. Well, as theta goes to 0, sine of theta over theta must go to 1 because what's the limit as theta goes to 0 of the cosine of 0? It's equal to the cosine of theta is equal to cosine of 0, which equals 1. And the limit as theta goes to 0 of 1 is equal to 1. So the sine theta over theta got squeezed in between those two. So there's your proof of this sine limit. Now let's practice some more of our epsilon delta proofs and see what happens when they get a little trickier like this. And that is the limit as x goes to 4 of x squared over 16. Okay? Okay, here's the problem with doing limits of quadratics and so forth. That if you remember again, our blue represented delta and red represents epsilon. And you can see to get within a certain epsilon, we're going to have to make delta small enough. But what we could count on before is over here, this ratio of delta over epsilon, epsilon over delta being a constant. Now you can see that's not the case because we don't have a line anymore. So I can't just say delta equals epsilon over 5. It's not always going to work. You can see as I get close in, the ratio seems to be getting higher. As I get further away, the ratio seems to be getting lower. So it's very hard just to say an easy answer to this, that if I want to get within epsilon, I'll pick delta to be epsilon over 5 or something like that. It's not going to work. We have a more complicated proof now. And so let's get back to that proof. So let's see how we're going to take this on. Let's start as usual with fx minus L is less than epsilon. Absolute value of f of x minus L is less than epsilon. So f of x in this case is x squared. The limit we're approaching is 16. Now, you can put in the specific value of epsilon now if you want, but I'm just going to keep it as epsilon like that. And now I'm going to factor out x squared minus 16 and x minus 4 times the absolute value of x plus 4 is less than epsilon. So there's the x minus 4. That's actually the delta statement. I call this the delta statement because this is what we get to pick. Pick a delta. Absolute value of x minus c is less than delta. So this statement over here is what I like to call the missing link. And now you can see why we can't just divide by a constant because this keeps changing depending on where we are in x, how far away we are. So we're going to build up and come up with the size of this thing by making an assumption. We make a first pick of delta to equal 1. And that's generally your best bet for a first pick of a delta. This gives you an idea of how big x is, so you can figure out how big x plus 4 is. So our first pick of delta equal to 1, leads to absolute value of x minus c is less than delta. So the absolute value of x minus 4 is less than 1. So x minus 4 is between 1 and negative 1. Add 4 to all three parts. 3 is less than x is less than 5. Does that make sense? Basically, we're approaching 4, and to get within 1 of 4, we're going to be somewhere between 3 and 5. If we pick delta equal to 1, that's our error in x, and we're saying we're getting within 1 of 4. So 3 is less than x is less than 5. Now, the whole point of this was to figure out how big the missing link is. So I'm going to add 4 to all three parts. 4 is less than x plus 4 is less than 9. I'm going to tack an absolute value on there. So the absolute value of x plus 4 is less than 9. I can do that because both endpoints are positive, so I know x plus 4 must be positive, so the absolute value is not going to change anything. But it's getting us toward our statement over here. Now here's the tricky part. I'm going to choose just to pick the right half of that inequality, and it'll serve us well because I'm going to multiply both sides by the absolute value of x minus 4. Multiply both sides by the absolute value of x minus 4. So now I get the absolute value of x squared minus 16 is less than 9 times the absolute value of x minus 4. Now I'm going to do a second pick of delta, and it's going to be based on getting 9 times the absolute value of x minus 4 less than epsilon. So x minus 4 is less than epsilon over 9. So I'm going to pick delta to equal epsilon over 9. By doing that, that'll force this, which will force this, which will force absolute value of fx minus L less than epsilon. See how that works by the transitive property of inequality? These two put together make absolute value of x squared minus 16 less than epsilon, which is what we want. Absolute value of x squared minus 16 less than epsilon. The thing is, though, this inequality here came from picking delta to be epsilon over 9. And this inequality here came from picking delta to be 1. Now, you can't have both. You have to pick your specific delta. So, what we do then, here's the compromise, pick delta to equal the minimum of 1 or epsilon over 9. So in this case, where you remember the original problem, epsilon was 0.003, epsilon equals 0.003. So let's compare 1, delta equals 1, or delta equals 0.003 over 9. That means delta would equal 0.003 divided by 9 is basically a third, so it's 0.03, right? I better check that. 0.003 divided by 9. Yeah, I get 0.0003 repetent like that. So we'd pick the smaller of these two, so you pick delta to equal 0.003 repetent. Now, in another problem, if I didn't give that specific epsilon, we'd actually stop here and say you always pick delta to be the minimum of either 1 or epsilon over 9. You make this special statement because it's going to change depending on what people pick. So if someone gives you something fairly small, you're going to pick epsilon over 9 for your delta. But if somebody picks something obnoxiously large, epsilon 9 is going to be way too large, and you'll just pick the 1 to be your delta, and then you'll make sure both statements are true. By picking the smaller of the two, we'll guarantee that both these inequalities are true. I know it's tricky, and it's going to take practice, but you'll get used to finding that missing link. Let's try it again on this next one here. Here we go. Limit as x goes to 2 of x squared minus 2x plus 1 equals 1. Yeah, if you put 2 in, you're going to get 1. But let's start with our f of x minus L is less than epsilon. Just switch to black here. So absolute value of x squared minus 2x plus 1 minus the limit, which is 1, is less than epsilon. Absolute value of x squared minus 2x is less than epsilon. So we have the absolute value of x times the absolute value of x minus 2 is less than epsilon. So x minus 2, that is your delta statement. Remember, it says x approaches c, and that'll be x minus 2. So here's the missing link, and this is the thing you have to figure out how big it is. So our first pick for delta equals 1. And we get the absolute value of x minus c is less than delta. So the absolute value of x minus 2 is less than 1. So x minus 2 is between 1 and negative 1. So that puts x between, add 2 to all three parts, 1 is less than x is less than 3. Now some kids go right to this. When they pick delta equals 1, they go right to this statement because they understand the concept. You want to get within 1 of what x is approaching. Within 1 of 2 is between 1 and 3. So you don't have to go through all this absolute value analysis. If you just want to go to that, I'll understand what you're doing. I'm going to keep doing it, though, until people get the hang of it. Now I tack on the absolute value. I'm going to pick just the right side. In general, that's true. If you do any polynomial of degree 2 or higher, you're always going to pick the right side of this compact inequality. Multiply both sides by the absolute value of x minus 2. And so we have the absolute value of x squared minus 2x, which remember is your fx minus L statement, is less than 3 times the absolute value of x minus 2. Now I'm going to go into red here and make my second pick for delta. And since I want 3 times the absolute value of x minus 2 to be less than epsilon, we pick x minus 2 to be less than epsilon over 3. So you pick delta to equal epsilon over 3. So, in general then, we're going to combine the two and say pick delta equal to the min, and you just say min for minimum, of 1 or epsilon over 3. In this case, somebody said, hey, epsilon's 0.001. So the minimum of 1 or 0.001 divided by 3 of 1 or 0.0003 reptant, the minimum of those two is 0.0003 reptant. So that's where we pick our delta to be, and we will make sure we're within that much of epsilon. Okay? Now in this case, for our last problem today, we're actually going to do a cubic. And we're going to do it in general too. Notice I'm not giving you a specific epsilon, you have to prove it for all epsilon. So we start off with the absolute value of f of x minus L is less than epsilon, as we do in all the epsilon delta proofs. And we put in our f of x, which is x cubed minus 5, minus the limit, which is 3, is less than epsilon. Absolute value of x cubed minus 8 is less than epsilon. Now maybe you remember your difference of cubes factoring, maybe you don't. Well, we know the x minus 2 statement, the delta statement, has to factor in this. So I'm going to try and divide 2 in to 1, 0, 0, negative 8. And sure enough, 2, 2, 4, 4, 8, 0, it works. So basically I can factor this in the absolute value of x minus 2 times the absolute value of x squared plus 2x plus 4 is less than epsilon. So here's the delta statement. We've successfully factored it out. The missing link is going to be kind of complicated though. And again, we start out with our first pick for delta. In this case, you just always pick 1. It works out pretty well. So the absolute value of x minus c is less than delta. Absolute value of x minus 2 is less than 1. X minus 2 is between 1 and negative 1. Add 2 to all three parts. 1 is less than x is less than 3. So we know how big x is now, but we want to know how big this thing is. So we're going to take it in 3 phases here. We're going to say, I'm going to square all 3 parts. So 1 is less than x squared is less than 9. I'm going to double all 3 parts. So 2 is less than 2x is less than 6. Add those up, and I get 3 is less than x squared plus 2x is less than 15. And now add 4 to all 3 parts to get 7 is less than x squared plus 2x plus 4 is less than 19. Okay? Tack on an absolute value because we know both ends are positive. And focus on the right-hand side. So the absolute value of x squared plus 2x plus 4 is less than 19. Multiply both sides by the delta statement. Then in this case, that's absolute value of x minus 2. 19 times absolute value of x minus 2. All of this multiplies out then to be what we're looking for. That is, we've already shown that that's equal to x cubed minus 8, right? Is less than 19 times absolute value of x minus 2. Now we go ahead and make our second pick for delta. And in this case, it's not just going to be 1. We want 19 times absolute value of x minus 2 to be less than epsilon, or absolute value of x minus 2 to be less than epsilon over 19. So therefore, our pick is going to be epsilon over 19. Now to finish the proof though, you have to say pick delta equal to the minimum of 1 or epsilon over 19. There you go. And we stop there because I didn't give you a specific epsilon in this one. This isn't true going to work in general. So if someone gives you an epsilon that's really big, like 100, you're just going to pick your delta to be 1. If someone gives you an epsilon that's really small, like 0.03, then you can use this, 0.03 divided by 19 for your delta. And that'll guarantee that both these inequalities, this inequality comes from delta equals 1. This inequality comes from delta equals epsilon over 19. By making sure I pick the smaller of those two deltas, I'll guarantee that both these are true, and then by the transitive property inequality, those two will force the absolute value of x cubed minus 8 to be less than epsilon, or, in other words, absolute value of f of x minus L is less than epsilon. And that'll be true for all epsilon. Okay. Flange out.